Hello, it's Mindy Bedrosian again, and we are looking at Chapter 10, which is the gas laws. Woohoo! These gas laws are fondly known as plug and chug because they are rather easy to plug in the numbers and chug out the answers. It's what describes the hot air balloon and how it works. So why are gases so special? They do have their own chapter, and they are considered rather special because they have unique properties that liquids and solids do not. For example, it expands to fill its container or vessel completely. It is easily compressed. It means you can squish it. Easily compressible. Mixes easily with other gases, and it doesn't matter what kind of gases it is, it will mix. And there are no intermolecular forces. They're too far apart. So some of the important equations that you need to know, this is pressure. Everything revolves around pressure, which equals force divided by area. The unit for force that we generally use is kilograms meters over seconds squared. It's also known as a Newton in physics. Joule, of course, kilograms meters squared over seconds squared. Similar, but not exactly the same. And the gas constants. R is 0.0821 atmosphere liter over mole K, or 8.3145 joules per mole K. You also need to memorize 760 millimeter mercury is the same as 1013 kilopascals, same as 14.7 pounds per square inch, 1 ATM, 760 torr. One of the equations you're probably not familiar with is molar mass equals dRT over P. D is density. You didn't learn this in regular chem, so let's do an example. Determine the molar mass of a gas with a density of 2.76 grams per liter, pressure of 743 millimeters mercury, and a temp of 25 Celsius. Pause. Plug and chug. You have to make everything similar. You need to change it to ATM because the R has ATM. 69.0 grams per mole is the final answer. An example of Dalton's law, again, pause after I give it to you. A container has 2.15 grams hydrogen gas, 8.32 grams helium, 4.17 nitrogen. The total pressure is 427.2 kilopascals. What's the partial pressure? Pause. All right, so you're going to change them all to moles and add them together to get a total. Remember, the bus always has to stop at Molesville. So we change them to moles, and we add them up. The total came out to be 3.29 moles. Now we're going to do what's called a mole fraction. We're going to find the partial pressure of each gas in this container. And for that, you're going to do a fraction. So for H2, it would be 1.06 moles divided by the total 3.29 moles times the kilopascals. That will give you the partial pressure of each gas. And here are the totals. You can check them to see if you got those. Standard temp and pressure are what you'll find in many problems, that it will always be 0 degrees Celsius and 1 ATM. So don't forget that. It's in many, many problems. So everything we know about gases revolves around the understanding of the kinetic molecular theory, which we've gotten in earlier chapters. It applies well to the gas laws. Things are in constant motion. All atoms and molecules constantly moving. Particles are tiny compared to the distances between them. And because they're so tiny and the distances are so big, there are no forces that they share between them. They exert no forces on each other. And the average kinetic energy is directly proportional to temperature. This is it. Temperature is a measurement of the motion of atoms and molecules. That's what temp is. So the gas laws are mostly plug and chug. Most of them you know. This is Dalton's P total, P1 plus 2 plus 3. This is Boyle's P1 V1 equals P2 V2. This is Charles, P1 over T1 equals P2 over T2. Now kinetic energy average you should know, 3 over 2 RT. Combining Boyle's and Charles is P1 V1 over T1. This is a combined gas law. And the queen of all the gas laws, PV equals nRT. So according to the kinetic molecular theory, there's a relationship between the average kinetic energy of any gas and temperature. Again, this is new. The lighter the gas, the higher the speed, the faster it goes. This is the root mean square velocity of a gas. Take the square root 3 RT over capital M. Capital M is the molar mass. Here I'm writing it out for you. Root mean square velocity. It's the molar mass in kilograms. And R is this R. Joules per mole K. There's also another one where you're comparing two gases, the speed. This is called Graham's law of effusion. R1 over R2 equals the square root of M2 over M1. And R is the rate of effusion through a pinhole of two gases. How fast do they move through it? You're doing a comparison. Now, for more like an AP question, stop at the end of the question and see if you can solve it. This is a highly toxic gas. I'm giving you the percent by mass, temperature, and pressure. And the 1.05 grams occupies 0.500 liters. What's the molecular formula? Predict its molecular structure. Predict the polarity. Give me all of them, stop, and do it. Here are some hints. Step 1, you can stop after each one. Solve for the empirical formula. That's step 1. And here's a little hint. Pretend you have 100 grams, since they gave it to you in percent. Step 2. Now that you've solved for the empirical formula, you will need to determine the molar mass of the molecular formula using one of the gas laws. Do you remember which one? This will give us the molar mass of the molecular formula. Here it is. That's it. So use that one now. Can you determine the density? You'll need to know the density. Do you have enough information for that? Step 3. Compare the molar mass of the empirical formula with that of the molecular formula. This should help you solve that. Step 4. Determine the Lewis structure and the formal charges on each atom in the Lewis structure. And step 5, determine the polarity. You should be able to do that. Here's the answers. And you can draw the picture of the Lewis structure. That's it.